Thank you so much for having me. It's really great, and it's really exciting to sort of hear about this workshop and everything. And I think this is a really interesting and nice time to sort of be thinking a little bit more about how we can, be like formalizing a lot and sort of modeling, given the gluttony of data that keeps becoming available. So I'm really excited to be here for this. And so today I'm going to talk about some of our research that we've done that's really focused on how we can model behaviors to understand infectious disease transmission. And I think a number of these things are going to get repeated throughout the whole workshop, but there's lots of different kinds of behaviors that can impact disease transmission. So if we think just about the risk of infection, some of those things might increase the risk of infection. You may have people who are traveling between places where maybe the disease is present to places where it's not, and so they might be able to introduce the pathogen. You can also have people who maybe have a large number of contacts compared to other people who don't have a large number of contacts. And for some things like sexually transmitted infections or respiratory infections, that might really increase your risk of getting infected. But there's also other behaviors you can adopt that will like mitigate that risk and reduce that risk in some way. So for example, I do a lot of work on malaria. So sleeping under an insecticide treated net might reduce your risk of malaria. And other things like vaccination. So even though you might be at a high risk behaviorally, if you're vaccinated, then you might not actually be susceptible. And then if you're able to do this on a population level and not just on the individual level, you may also have some indirect benefits. And so we, like historically, in the most simplified sort of compartmental models that have been used, really simplify a lot of these behaviors that are driving transmission, and in particular, really simplify the heterogeneity amongst the population. So the most classic example is you have people susceptible, infected, and then recovered. This is the SIR model that during the pandemic was even on the news, which was strange, where you have people who are, might get the disease, have the disease, and then are able to recover from the pathogen. So this is like the core of a lot of infectious disease modeling historically, and still, a lot of models are kind of based under these simple assumptions. And one of those about behavior is that people mix uniformly or mass action. So the idea is that all of the people who are susceptible and all the people who are infected all have an equal chance of interacting with another that could cause disease transmission, and that's just dependent upon like the densities of those different groups. We know that's not very realistic. Like people, I think like like nursery school kids are like that maybe, where they're actually like susceptible infected kids in effectively a box roaming around with one another, but we know that's not how the actual population works. And so a lot of work has also been done about what kinds of data can be used to try to break that assumption of sort of everyone's equally likely to be in contact with one another. And one of the most famous examples is like the initial polymod study, or there have been a number of them done after that, where you have this age assortivity mixing, where you have people are more likely to be in contact with other people of their same ages, and you see some differences, of like people of childbearing age and younger individuals. But all data is not necessarily created equal, and so some of those might actually be biasing how we're breaking those mass action assumptions. And so this is work that was done that was looking at just vaccination rates from a few different sources. So things like social networking sites like Facebook, a census, which would be sort of like powered to, particularly designed to be representative, and other things like using online polling firms and things. And the CDC benchmark is shown in that gray line, and you can see that when you use these different data sources, you might get very different rates of vaccination, upwards of 20% different, which depending on the pathogen could give you a really different estimate. And this is all just based off of who gets in these data sets and how are they being used. So we often fit models to those to be able to try to better improve our estimates of disease transmission. And so I'm going to talk a little bit about some of the modeling work that we've done that's really focused on behavior. And I'm going to focus on two different aspects of behavior that we've worked on. So the first is better understanding population level mobility. So how can we better understand how are people traveling? How do people travel differently amongst the population? How do they travel differently in different countries? And then I'm going to talk about some of our work that we've done that's on the behaviors of people who inject drugs, or PWID. PTSD. And in particular, I'm going to talk about how we can leverage some of these data sets to make more realistic behaviors to better understand hepatitis C or HCV and HIV transmission. So to start with the mobility bit, so infected individuals are able to introduce pathogens into susceptible populations. And this has been happening as long as people were coughing on one another and people were going places in the world. So this is a paper that was done a number of years ago that is looking at some historic outbreaks all the way back to the 2nd century of the plague, and mapping sort of where those cases were found and sort of the routes that those were getting mapped between. And so you have colonization, which remains bad, where you had smallpox, measles, and others getting introduced into other parts of the world. You have malaria being introduced from the slave trade. You also have things like the first SARS-CoV-1 epidemic that was primarily driven by international travel. So people moving diseases is not a new phenomenon. But what has sort of changed and shifted is kind of like, how do we want to understand that process? What timescales do we want to understand that process? And how can we use that information in more real time? So, you know, when you're thinking about like a canonical outbreak where, you know, you have limited community transmission, you have widespread community transmission where you see it all going up, and then you have lower ongoing transmission. There's sort of different questions where mobility would play a role and where you'd want to understand that. So when you don't have a lot of community transmission, you may be interested in trying to see what's the risk that it's going to be introduced in the population, and what might be the source of those introduction events. As you have community transmission, like during the pandemic, when you were interested in, you know, they implemented non-pharmaceutical interventions like stay-at-home orders or travel restrictions, then you may want to measure, are people actually staying at home? Do you actually see a reduction in people's behavior that should be decreasing transmission? As it's going on, you lift some of those, then you might want to also be able to see, has travel resumed and what might be the implications for the disease? And then as you have sort of lower ongoing transmission, you might be interested in understanding the risk of things like reintroduction events. So for lots of different pathogens, we might be interested in these different things. You know, measles, for example, has resurged in many parts of the world. And so better understanding, is it going to be introduced here? Or if we're able to increase our vaccination rates, what's the risk that it will be reintroduced, is just one example. So this is work that was led by Katie and Natalia a number of years ago, where we conducted a systematic review of population-level mobility data that was used to understand SARS-CoV-2 transmission. I would recommend never doing this. This did not spark joy in any of us, but if anyone wants all of this curated data, we have it and we don't like it. So we focus. Like everyone and their mother was suddenly an expert in epidemiology during the pandemic. And they also, in particular, were an expert in things like how people move, because now they use their lived experience of ever going on vacation with their now newfound knowledge of being an epidemiologist. And so there was a lot of papers that were published. And so what we did with a whole team of people is trying to see, like, what did we learn, or what information was gained, or how did that bring apart any new knowledge. And so from these papers, we extracted information about, you know, the authorship, what was the scale of analysis they did, where did they do it, what was the goal of their paper. You know, some papers that focus on mobility are trying to estimate that introduction rates, others are trying to look at what could be the impact of different travel restrictions and things like that. All of the papers we really focused on had to use some sort of mobility data about populations. So we didn't include any of the papers that were some of those like first case reports where, you know, like the person was like skiing in France and then there was like a small outbreak. These were all like population, so like 1,000 people or more. And then we looked at how they actually analyzed these data, how they brought the data and the infection information together and things. And so we screened about 5,000 abstracts, and we restricted it just to the first year of the pandemic. Overall, we analyzed like in like for the review, about like 200 papers were included. And all of these papers needed to include quantitative data about mobility of populations, and they had to focus on the transmission of SARS-CoV-2. For example, there are a number of papers that came out at this time of sort of effects of having COVID that impacted your gait and mobility in that way, but those weren't the things that we were really interested in. So overall, what we found is that right from the start, people were using pretty much any kind of data that they wanted to use and that might possibly be evaluated. We thought that because some data sets were becoming available at different times, there might be temporal trends, but really, from all the different sources, be that things like Facebook or Google, mobile phone data or flight data, there were papers being published on pretty much all of these types of data sets throughout that entire first year. We also found that different data sets would be used to calculate different types of mobility metrics. So oftentimes when we think of mobility, we think of just how many trips occurred between a location A and a location B. But some of them also were calculating, how much people were spending time at home, how were people clustering, how many people were away from home or spending time at different locations and things. And really, there are very few instances where one data set was only used in one particular kind of metric. It was sort of used across the board. What was interesting of what we found is that almost none of these papers modeled mobility, whereby they took the data and they applied some sort of mathematical or statistical model to that data and used that in their analysis, as opposed to taking the counts of the data and then directly using those values. And so of these papers that we analyzed, there were only 6 instances where someone used a mechanistic model in particular. There were a few more statistical models, or some smoothing. Smoothing was quite common in the data, but almost none of them were mechanistic. And almost none of the papers evaluated if you even needed these data. So almost none of these papers were saying this data, I'm having a null hypothesis that I don't have the mobility data, and this is kind of what I need in addition to having that data set. So I think that for this group in particular, that's really important because a lot of those data sets are going offline, or they're not being made available anymore. So there's a couple of companies that sort of are still making their data available and still producing those data sets. But in general, the vast majority of data that was being used, you might be able to get historic data, but they're not making new data available. And since there was very little advancement in terms of sort of modeling those processes to sort of improve our mechanistic understanding of what's driving those behaviors, it means if the data are not available, most of those analyses would not be able to be done because those analyses were highly reliant upon those data. After seeing so many abstracts, some could argue they didn't all need to be done, but it's still probably like a good thing to think about. So in sort of the infectious disease kind of literature, the most common way that people think about mobility is something called a gravity model that was originally developed in the 1920s from transportation that was looking at commuting in the US and then later Europe. And so this model is sort of ubiquitous in the field, mostly because it's really, really simple and it seems to do an okay job. The actual structure of the model can differ. People add in different covariates and do it different ways. But effectively, the model is structured that they try to estimate the number of trips between locations. They say the attractiveness of a place will be based off of how big that place is, and then how far away that is your deterrence factor for that. There are iterations of this, like constrained versions, ones that take into account economic opportunities and how much, like the geography of places and things. But those all kind of just boil down to how can I measure the attractiveness of wanting to go to a place divided by or subtracting sort of that deterrence of how hard it is to get between those places. And so I'm going to talk a little bit about some sort of projects that we've been doing that are sort of trying to look at this model and others to better understand mobility. So first, I'm going to talk about work that NOAA has been leading, where this is a pretty simple problem. So a lot of these data come aggregated, which means I know that there were 100 trips between locations A and location B. But oftentimes we don't have the individual level data to know if 100 people each took 1 trip or if one person took 100 trips. So you could have the instance where you see 5 trips that are getting measured between different locations, where you have everyone taking one or one person taking all of them. And that's going to have really different risks of importation depending on who's infected. So for example, if your infection is something that is highly concentrated in particular parts of the population, where it's not as justifiable to make the assumption that everyone might have an equal likely chance of being infected, that's going to have a really different importation risk in your population. So for this work, Noah's been analyzing individual level data. A lot of it's come from Zambia. That's trying to look at individual level mobility data and trying to look at this phenomenon. And in particular, what he has done is he has fit a model that just looks at what proportion of your population is going to travel, and then given those people are traveling, what's the distribution of trips that they're going to take. So it's a pretty simple structure of the model. You can have that, there's like a very clear decay, everyone's taking few trips or things, and he's fit all this to the individual level mobility data. To be able to better describe sort of, if you have a certain number of trips, what's the distribution of how many people are going to take those trips and how many people are going to take multiple trips. Another project, so this was other work that was done by Natalia as part of her PhD. So as the COVID example showed, there's a lot more data sets that are available, but there are fewer methods that are thinking about how you can leverage the fact that you might have multiple types of data for the same location. So for example, I might have information from mobile phones in a population. I might have information about flight patterns, but those are going to capture very different kinds of movements in the population. The people who are taking trains between locations versus the people who are flying between those versus the people who might be taking cars are not necessarily all capturing the same types of travel, the same people traveling, even though they might have the same origin and destination. And so if you think about different kinds of data sets, they also might have very differences in terms of their spatial granularity and the time period that those are being taken. You can have some things like GPS logger data where you put GPS loggers on people or use people's phones where you're tracking like very, very granular movements. You can have other data that's like surveys where you might ask people where they went in the last week, or things like flight data where you might just know that this many passengers went between this origin and destination. And all of those data sets are going to have different kinds of biases. You might have some things that are supposed to be like not as biased and population representative like the census, but they're not taking those on a very regular basis. And so what Natalia worked on is how can we combine these different data sets into a very similar model to the one that Noah's worked on, and the gravity type model of just trying to figure out how many people would you estimate are traveling, and then given that, where's their destination from these different data sets. And so she just made sort of like a gravity-like model that used some priors from one data set to fit the next data set. But it's very similar in structure to that gravity model, where she sort of like combined different kinds of data sets. So if I use a prior from survey data, how does that change sort of my fit when I'm looking at trying to fit like mobile phone data for all these different combinations of different data sets? Because we had all these different data sets from all the same place. So this is just one of the results from those. So the DHS is the demographic health surveys, which were conducted by USAID in many low and middle income countries that were collecting information predominantly about children. And those were intended to be sort of like representative of children in those populations. Facebook data that is measuring people who have Facebook on their mobile phone, an app measuring their locations, mobile phone that's looking at when people are using data or sending or receiving calls and text messages, and then a survey that was also conducted. And so sorry, I just landed this morning. The x-axis is the same across all of them, but you could see if you used one of these data sets versus the other, you would have a really different probability that those people would be traveling. So if you use something like the mobile phone data, you would estimate a much larger volume of trips than if you use data from like the demographic health surveys or the travel surveys. And Natalia did a number of things to try to make them even more comparable, looking at where we have the exact same data in the same places, trying to adjust for some of the age and demographic biases of each data set. And so overall, what sort of Natalia found is it didn't really matter what other data set you were using. If you were using the mobile phone data in any way, shape, or form for your fits, that kind of completely dominated all of your fits. So it did not really matter what other data set you threw at it. If you used mobile phone data as your prior, that was always going to be kind of like the most important thing on driving your posterior. And so Natalia also did some measles simulations using this, and then we actually found that there very little variability in those like the outbreak dynamics with all of those different data sets and all of those different models. So even though you had very different estimates, estimates with different kinds of data, if you use the mobile phone data, that would kind of give you this effectively the same estimate. And then in your epidemic simulation, you were getting almost exactly the same outbreak dynamics. The last project that I'm going to talk about is work done by Jasmine, and this is really looking at trying to make data and models available, particularly in data poor settings. So, you know, during the pandemic, we got lots of different data in the US, but there's still lots of places where data is not available. So, for example, in that systematic review, it was like a single-digit number of papers that were about sub-Saharan Africa. And I do a lot of work in malaria, and so we're particularly interested in understanding how those patterns move or not, or different or not. So Jasmine has been fitting Facebook data or survey data or mobile phone data to all these different countries and all these different things and trying to look at how different are those estimates with different structures of models. Oftentimes you get very different estimates based off of what kind of model you're using. So this is just a subset of all the different sort of like commonly used models that are sort of like that gravity model, and you can get really, really different estimates in terms of like how many people are traveling and how different that is from the data based off of the model structure that you're using. And so she's also been simulating these to try to better understand how that impacts the transmission dynamics. So now I'm going to shift gears a little bit and talk about some of the work that we've been doing about the behaviors of people who inject drugs. So this is very different population, very different from sort of these population level mobility questions. But people who inject drugs, or PWID, they bear a disproportionate burden of blood-borne viral diseases, and they face a large number of intersecting vulnerabilities that result in very poor health and social outcomes. So a lot of this work has been done in India and in Baltimore. So I'm based in Baltimore. If anyone has seen The Wire, parts of Baltimore are still like The Wire. And so this study has actually been going on since 1988, and a lot of the issues that have that were in The Wire are still issues today about sort of the impact of drug use, the impact of policing and things in Baltimore. And so the left-hand side is a figure that just shows from this study called the ALIVE study, you know, individuals who inject drugs are 22 times as likely to be infected with HIV, and they had like about a 5 times mortality rate. And so this estimate of 5 times mortality is also not necessarily completely up to date with the fentanyl crisis, but you can see that, you know, it's a very stigmatized, it's a very disadvantaged population that have a lot of intersecting vulnerabilities that make them predisposed to have poor health outcomes. And so I've been lucky since I've been at Hopkins to be able to work on this study called the ALIVE study that is an ongoing community-based cohort in Baltimore City since 1988. Originally, it only enrolled people who so it only enrolls individuals who have a history of injection drug use who are adults. You don't need to have HIV to be included in the study. There are semi-annual follow-up visits that include a wide range of assessments in terms of asking questions about behavior. They do a lot of like clinical evaluations and laboratory tests. And in total, you know, there's been about almost 6,000 participants in this study. And the median visits is about 7 per person. But this study is like, well, very integrated in the community. There are people still in the study who started in the original enrollment period from the study. And so there's this really wealth of data about being able to understand how injecting behaviors and seeking care behaviors have changed also as the drug use and drug markets have also changed in the population. So just to give you a sort of like reference about sort of, so these are the incidence rate ratios for hepatitis C shown in red and for HIV shown in blue. Overall, the hepatitis, about 40% of the 40 to 60 days or 65% of the individuals who are currently active and alive have hepatitis C. And so it's a very common infection. There is treatment that is available, but if you're still participating in the still risky behaviors, when you complete treatment, you're likely to get reinfected. And so we worked on a study that was looking at what is the impact of COVID-19 on this population and on the risk of these infections. So at the beginning of the pandemic, there was a lot of concern because a lot of health facilities and care facilities were closing or had to divert their resources. So things like harm reduction facilities where people might be able to go to get treatment for opioid use disorder that would reduce their injecting behavior, places where people could get safe syringes were often closed or unavailable or had very limited hours. There was also a lot of concern because a lot of HIV and hepatitis C testing was not being done because a lot of, everyone was working on the pandemic. There was a lot of concern about all of this. And so even when places were able to reopen, there was also concern that they were reopening in very strange and erratic hours. So maybe normally they would be open every day, and now they're only open like Tuesday afternoons. And so getting that information to the population that needs those services could be very difficult. So there's a lot of concern that this might be very bad for this particularly vulnerable population. And so in general, there's a lot of modeling projects that were done, and pretty much they all uniformly showed that there would be an increase in hepatitis C and HIV amongst people, primarily from not being able to access clean syringes. And so this is modeling work that we were not a part of that looked at what would happen if those health resources were permanently closed or only temporarily closed, but pretty much always any of the modeling work that was done showed that there'd be an increase in HIV and hepatitis C. But when we actually have looked at the data, and as there have been over time, there are fewer and fewer reporting biases. Like initially, we thought a lot of that might be reporting biases, but now it does appear to be that there were actually few locations in the US that reported substantial increases in hepatitis C and HIV. So despite a lot of concern that there would be large outbreaks, there were outbreaks and increases in some locales. But in general, across the US, we did not see a giant surge in hepatitis C and HIV. And so we were really interested in trying to understand why this may have happened, because in Baltimore, a lot of these services were closed or had very limited availability. And when they reopened, they didn't open at full capacity. And so this is work that was led by Jasmine, where she developed an individual-based dynamic network model of injecting in sexual partnerships based off of this alive data, so this longitudinal cohort data. And in particular, we were looking at what would happen when you reduced people's services for things like medications for opioid use disorder or MOUD and syringe service programs and HIV and hepatitis C testing and treatment. And so she simulated a model that was very similar to the demographics and characteristics of the alive population. So it had similar cessation patterns, it had similar uptake of these different kinds of interventions, similar demographics, similar overdose rates and mortality rates. And so from those modeling, so we modeled sort of a range of different interventions. And so this is just one showing HIV prevalence, where orange is the baseline, and then that purple line is when you had a service change. So like a lot of those other modeling results, we did see a similar thing that if you close a bunch of services, pretty obvious, you don't really need like our level of modeling to be able to do this. If you close a bunch of these things, HIV and hepatitis C would also go up. But because we were able to leverage sort of these really rich data from the alive cohort, we were able to actually look at how people's injecting practices changed. So we were not looking just at what happens if things close, but are people changing their injecting behaviors? And so what we had people who were in the study who we were able to follow up pre and post pandemic. So you had some people who are in early cessation groups. So they're going to stop injecting within a short period of time. They're not necessarily going to become like a persistent injector, or maybe there are periods of time that they stop, but they're sort of consistently always restarting when they're stopping. And so what we actually saw is that a lot of these individuals sort of moved into this post-pandemic early cessation group who would have been normally been a quite high risk group. So the people who are in blue are sort of the lower risk individuals. They're people who are going to stop injecting much earlier versus the people who are going to be relapsing multiple times or sort of consistently be injecting, which is shown in all of the other colors. And what we actually saw was a lot of people were shifting their injecting behaviors and started using less. And they also, the individuals who were continuing to inject did increase their injecting frequency, but it was just a smaller proportion of the overall population. We were concerned that this is sampling bias. You know, if there are people who we are able to contact during the pandemic, they might be individuals who are much more stable. They might be individuals who are much more already likely to get into treatment or to stop injecting a lot earlier. And so we did a lot of sensitivity analyses to see, is this just effectively a survival bias? The people that were able to contact after the pandemic, the people who didn't move out of the area or who were not able to contact for another reason, are those just more stable individuals? And what we're seeing is those individuals. So we did a bunch of sensitivity on analyses of these, and we don't think that's what's happening in this population, that we're only collecting the data from individuals who are more likely to have those early cessation patterns. And so not just injecting behaviors changed, but others did too. So people were injecting with fewer people, fewer other individuals. People were more likely to reducing sort of their probability of injecting or sharing syringes with other people post-pandemic versus pre-pandemic. And then so when we actually include the service disruptions with the injection behaviors, what we saw in our model is that doesn't necessarily the end result is HIV and hepatitis C wouldn't necessarily have gone up. So in some simulations, it did still go up, but in general, we saw a number of simulations that it wasn't necessarily going up from baseline. And so this just provides some idea and some suggestions about why we may not have seen sort of those large outbreaks or large increases in HIV and hepatitis C prevalence or incidence, is if individuals were also changing their injecting behaviors. When we actually look at the alive data, because when people come in for those visits, they're regularly tested for HIV and hepatitis C, we do actually see that the prevalence appears to be going down. It's still a little noisy. So that red area is sort of that pre-pandemic period from 2018 to 2020. And then the alive data post-pandemic, we do see that there is a quite sharp decrease down, but there's not necessarily a huge number of respondents in each one of those surveys. So what we found by integrating these sort of like more detailed behavioral data is, there might be these counteracting forces where you might have service disruptions that are preventing people from being able to get care, but that's coupled with these behavioral changes that is sort of mitigating the risk. So the service disruptions might be increasing their risk, but that has to be counterbalanced with behavioral changes that could be decreasing their risks. So I am not a qualitative researcher, but one of our collaborators on this project is. And so in qualitative work, some of the reasons why they found that individuals have decreased their injecting behavior or who they were injecting with, particularly at the beginning of the pandemic, was it was a lot harder to be able to purchase drugs because people weren't out. People were inside a lot more, there weren't just people outside. And the drug supply was a lot more erratic, at least in the 2020-2021 period, because a lot of like shipping and things in general were sort of disrupted. That also disrupted the drug supply too, at least in Baltimore. So just some conclusions. So, we're really interested in how we can think about how you can make better understanding of behavior, be that through different kinds of models, different kinds of model structures, and other types of data that's available. In a lot of disease modeling, we're either sort of shifted over that we're highly reliant upon these really detailed data sets that became available, or we use these like pretty simple models, and there's not a lot that's sort of advancing from those pretty simple models into something a little more sophisticated whilst leveraging that data, but it's still something that's going to be like easily reproducible or used in a lot of different contexts. And so models, and the other sort of benefit of models is if that data set is taken away or you're no longer able to access it, it is going to be able to provide you a way that you could at least use like an informed way of better understanding what behaviors might be driving disease transmission. But I think a lot of work and a lot of effort has been done to sort of think about like population level models, like what happened during lockdown and things like that. But, you know, understanding the behaviors of particular populations is going to be increasingly important if they're ones driving transmission patterns. You know, as we have more data that's available and a better understanding of and can describe the heterogeneity amongst the population, the better we can map sort of that population at risk or that population susceptible or infected to sort of the actual disease transmission. I think that's going to also help make these models a lot more realistic. And lots of people were involved in this work, and also a number of funders.